Seeing a star a few years before it blew up, so right at the very end of its lifetime, is kind of an amazing thing to see, to know that that star is about to explode. Yes, so there was this breaking news of a possible supernova in M95, and obviously there's now more information about it. We now have confirmation that there really was a supernova in M95. Supernovae, when they're first discovered, or at least they're possible supernovae, they're given a name PSN followed by a long telephone number that just basically says where they are on the sky. But once they're actually confirmed as supernovae, they get their own names. So this is now supernova 2012 AW. And the 2012 is obviously the year, and the AW is the way this works. You sort of cycle through the alphabet. So the first 26 supernovae were A to Z, and then you start going AA, AB, AC, AD, and so we're all the way through to AW. So this is the 49th supernova of the year, and here we are in March. So presumably we're going to go through the alphabet several more times before the end of the year. So it's happened in M95, nice, relatively nearby barred spiral galaxy, which creates lots of exciting possibilities. It's sufficiently nearby we can actually see individual stars in this galaxy, and that gives us this exciting possibility of actually seeing the star that blew up.
And what's happened?
And they have indeed seen the star which has blown up. Some astronomers at Queen's University in Belfast and various collaborators around the world went into the archive and found the Hubble Space Telescope picture of this galaxy, and were able to match that up with a post-supernova picture of the galaxy. And you sort of match up the position, well, there's where the supernova is, and then you look really hard in the Hubble Space Telescope image, and you can actually find the star that blew up. So here's the whole of the Hubble Space Telescope image. It's this sort of rather strange shaped field of view just because of the detectors in this particular camera in the Hubble Space Telescope. This is the region where the supernova blew up. And so notice this red blob here, that's not actually the supernova or its progenitor, but it's a useful sort of calibration point. So if we then zoom in on that little bit, so it's before the supernova blew up. So there's the red blob we had before. This is the zoom in on that area, and this is the error circle of where that supernova is likely to have been. And of course, there's actually only one object within that error circle. So this is the star which then blew up as supernova 2012 AW. And having now discovered it, of course, you can now start analysing the properties of the star before it blew up. And so one of the weird things about this particular star is it's actually very red. You can sort of see that in the image. And it looks like it's a relatively low mass star that blew up. It's about 8 times the mass of the sun. It's quite hard to go from what you can actually observe in these galaxies, of these stars, to actually figuring out the properties of the star itself. It's pretty much at the minimum. I mean, if you read in the textbook and ask, well, you know, what's the minimum mass for a star to blow up, they all say around 8 solar masses, and it looks like this was at least the original star before it started, because before it blows up it actually starts shedding some of its outer layer, so it's lost some weight before it blows up.
That looks like about 4 or 5 pixels to me in a picture. How can you tell that about that star? How can you tell its mass from such a small amount of information?
So you can't see anything really about the spatial structure of the star. It's completely unresolved. It's just a little dot in this image, and as you say, it's a few pixels across. But what you can analyse is the brightness of it and the colour of it. So by taking the pictures in several different filters, you can actually analyse whether it's a very red object or a very blue object. And because we know quite a lot about stellar evolution and what properties stars ought to have at different stages of their lives for different masses of stars, in terms of how bright they are, what their colours are, you can at least crudely convert those things you can actually observe into this sort of fundamental property of the star of what its mass is.
When the astronomers from this European collaboration sent me that image, I was very excited. I was like, amazing, that's the star before it blew up. Was I right to be excited, or is this a dime a dozen?
They're certainly not a dime a dozen, and this is hard work to do this, to find these progenitor stars, and also you can really only find them in nearby galaxies, because it's only nearby galaxies you can actually pick out the individual stars. And so this is still a sort of a developing industry of finding progenitors of supernovae in this way. And so yeah, you're very right to be excited about it, and just seeing a star a few years before it blew up, so right at the very end of its lifetime, is kind of an amazing thing to see, to know that that star is about to explode.
So even you, the old jaded astronomer, do you get excited by this?
I think this is real. I mean, this isn't the science I do, but it's one of those areas of science where once in a while when I look at what these guys are doing, it is kind of something I wish that I was doing. Yeah, it's very neat stuff. So what will happen over the coming few months is that basically the supernova will just start to fade away. The initial explosion will fade over time. And you can learn something about the properties of the star that blew up by following that, that fading away, by taking spectra, by splitting the light up into the different colours at different stages, course, what's happening is the star's kind of expanding into space, and as it expands, you see different layers within the star as it's kind of becomes, the gas becomes thinner and thinner as it spreads out. So by following the evolution of this supernova, both in terms of its brightness, perhaps more fundamentally in terms of what its spectral properties are, what elements you see and so on, we'll actually learn something quite fairly fundamental about the properties of supernovae. So there'll be one of these things left behind called a supernova remnant, and they come in all sorts of shapes and sizes. There are supernova remnants we study in great detail in the Milky Way, like the Crab supernova remnant and the Vela supernova remnant and other remnants like that. They tend to have rather different morphologies, and again, it's probably something to do with the subtleties of the explosion. But it's not a process we understand sufficiently well to be able to predict exactly what kind of remnant you're going to get out of this explosion. So this is a video that somebody has put up on Flickr that they're allowing us to show in our video here. Here is M95, quietly minding its own business. This is a sort of time-lapse series of pictures over a couple of nights, and then suddenly the supernova appears down there.
A few days ago it was possibly a supernova, now it's confirmed. How did they confirm it?
So the way you identify these things is by taking spectra of them, so by splitting the light that the supernova is giving up into the colours of the rainbow and analysing the light. And different types of supernovae have very characteristic spectra. So this particular type of supernova, a type 2 supernova, which is from a massive collapsing star, has strong hydrogen lines in it. The other main type of supernova, the type 1 supernovae, don't have hydrogen lines in them. So in fact, that's what the terms mean. And so this one was analysed, they took a spectrum of it and found it had these very strong characteristic hydrogen lines of a type 2 supernova.
What is it about a type 2 that gives it a different spectrum to a type 1?
So really what you're seeing is a type 2 supernova is just a star exploding at the end of its life. And of course the outer layers of that star are just pure hydrogen because nothing has happened pretty much. Well, there's some helium from the Big Bang, but mainly the outer layers of that star are made of hydrogen. And so what you're actually seeing is as the star blows up, the light of the explosion shines through that hydrogen, and you end up seeing the hydrogen absorbs light at very specific wavelengths, and you see that absorption of the outer layers of the star as the explosion's going on sort of beneath them. But type 1 supernovae have typically lost all those outer layers of their hydrogen before they blow up, so you don't have those outer layers of hydrogen to be sort of lit up by the explosion, so you don't see the absorption from hydrogen.